Hello everyone, this is Vasishta from Aerobi section. Today I am going to explain about combustion stability in aerospace propulsion. So, what is combustion stabilities in aerospace? Generally, combustion instabilities are the physical phenomena occurring in a reacting flow, in which some perturbations, even very small ones, grow and then become large enough to alter the features of the flow in some particular way. Like when we take an engine of a when we take a jet engine, the combustion which is happening on the engine may be instable due to some fuel mixture, different fuel mixtures, and some oxidizers and etc. Because of that, the eddies will form, the vibration will form into the engine, and sometimes engine may get blown due to combustion instabilities. What causes combustion instability? In the simplest way, combustion instability can be thought as the pressure swings in the engine caused by the multiple streams of liquid oxygen and rocket fuel combining and igniting at extremely high pressures in such a way that causes violent vibration. As I said earlier, due to the violent vibrations which causes an drastic damage to an engine, the main factor that is acting on this combustion instability is the pressure. The higher the pressure, the more the instability will be and greater the damage. Coming to the introduction of this topic, chemical propulsion system depends fundamentally on the conservation of energy, conversion of energy stored in molecular bonds to mechanical energy of a vehicle in motion. Combustion of fuel and oxygen in the first stage, burning takes place in the vessel opens in only to admit reactants and to exhaust the hot products. Higher performance is achieved by increasing the energy release per unit volume. For example, probably the highest power density was reached in the F1 engine of the Apollo vehicle, 146.4 gigawatt. The power density in solid rockets are much less. For cylinder bore, the valves are approximately 0.2577 gigawatt by meter cube, where R is the linear burning rate, typically a few centimeter per second, and D is the diameter. Thus, the power density rarely exceeds 1 gigawatt per meter cube. An afterburner on a high performance fighter may burn fuel at the rate of 75,000 pounds, which is approximately 34,000 kilograms per hour, generating roughly 450 megawatt for a short period in a volume of less than 2 cubic meters. These are indeed very large power densities. To appreciate how large, consider the fact that average power consumption per person in developed country is about 4 kilowatt. For United States, with approximately 250 million people, the total power consumption is about 1000 gigawatts. Hence, for the few minutes, the 5 F1 engines in the first stage of the Apollo produced a power equivalent to about 75% of the entire electrical consumption of US. In a very small volume, we cannot be surprised that such enormous power densities should be accomplished by small but annoying fluctuations. Integrated multi-fidelity modeling has been performed to combustion instability in aerospace propulsion, which includes the level of analysis which includes two levels of analysis. First, computational fluid dynamics using hybrid RANS LAS simulations for underlying physical investigation, highly fidelity modeling. Second, model decomposition technique for diagnostic analysis and validation. Third, development of Flume responsible model using reduction techniques for practical design applications, lower order model. For the high fidelity modeling, the relevant CFD code development work is moving towards combustion instability prediction for liquid propulsion. A laboratory scale single element lean direction engine (LDI) gas turbine combustor is used for configuration that produces self-excited combustion instability. The model gas turbine combustor is featured with an air inlet section, air plenum, spoiler, Venturi, Venturi injector assembly, combustion chamber, and exit nozzle. The combustor uses liquid fuel and heated up to 800 Kelvin. Combustion dynamics investigations are performed with the same geometry and operating conditions concurrently between the experiments and the competition at both high and low equivalence ratios, which is zero point 0.6 and 0. The simulation can reach reasonable agreement with the experiment with measurements in terms of pressure signal. As we know, CFD analysis, computational analysis of the performed using the acoustically open geometry to investigate the characteristic hydrodynamics in the combustor, both constant and perturbated inlet mass flow rates. Two hydrodynamic modes are identified by using dynamic mode decomposition analysis, vortex breakdown bubble, and a swirling model. Following that, the closure geometry simulation results are analyzed in three steps: detailed cycle analysis and the important couplings in the combustor, acoustic compression analysis, and state of breakdown. The frequency based on these are ROM, reduced order model, which can which can be used in engineering level to provide a efficient prediction of combustion stability for practical design. Once the ROM is established, it can be used as a lower order test bed to predict data results within certain parametric range. Moreover, certain criteria during ROM development are established about a necessary number of POD modes that should be included to guarantee a stable ROM. The need for the numerical discretion seemed to be consistent between the original CFT and the development ROM. Furthermore, the predictive capabilities of the resulting ROM were evaluated to test its limits and to validate the values of applying broadband forcing to improve the ROM performance. In part 2, the exploration is extended to a vector system of equations using the one-dimensional Euler equation is used as model equation. The numerical stability issue is identified during the ROM development, the cause of which is further studied and attributed to the normal. As we have seen earlier, the frequency-based DMD technique provides modes that corresponding to all frequencies for the lower order modeling. Fundamental aspects are examined to study the POD derived eigenbase are in turn which used in conjunction with a Galerkin procedure to reduce the governing partial differential equation. So an ordinary differential equation consists of the ROM. The ROM is established and can be lower restrict. The detailed assessment is performed on the method in two parts. In one part, a one-dimensional scalar reaction advection model equation is used for fundamental investigations, which include verification of Ford eigenbase basis calculation and the ROM based development process. As we can see, why is combustion stability a problem? Combustion stability causes severe damage to the engines, which cost crores of values or millions of dollars. Combustion instability can cause severe vibration, increased localized heat transfer, decreased performance, and other problems. In especially severe cases, the engine structure or propulsion system may be damaged or destroyed. As I told earlier, Combustion stability is a serious problem and a serious problem which destroys the engine and the rocket that the combustion chamber with the propellant and exhaust. So this is all my explanation about the combustion instability. Thank you.